Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over how to write nuclear reactions or nuclear equations. So let's get into this. But before we begin, please like this video, share this video, put a comment in the comment section, subscribe to my channel if you like what you see, and that way you will get notified by any other videos I put out. Okay, let's get into this. So we're going to write nuclear equations. So there's different types of nuclear decay. There's alpha decay, the beta decay, gamma emissions, gamma radiation, things like that. So we're going to go from the word equation here, and we're going to write out what the equation looks like for a nuclear reaction. So for number one, they're asking us write the nuclear equation for the radioactive decay of polonium-210 by alpha emission. So we're starting with what is called the parent atom or isotope. This is polonium-210 in this case. And then we want to figure out what the daughter isotope is from the alpha emission. So we need to know what type of emission we have. In this case, it's alpha emission. So if you remember, alpha emission is a nucleus of a helium atom. So it's just 2 protons and 2 neutrons. And so using what we know about the alpha particle, we can figure out what's left over. So what you do is you begin with what you're given with. So this is our reactant. We're starting with polonium-210, and it's going to break apart and produce some products here. One of those products is an alpha particle. So 210 is the mass number. So when we write our symbols for these elements, we're going to need to know the mass number and the atomic number as well. And we're going to need our periodic table. So here I have a periodic table right here, so we can do our work. All right, so polonium is pure. Let me use a different color. So we put the symbol PO. This is the mass number. The mass number goes on the top left corner. So that's going to be 210. And then the atomic number goes in the bottom left corner. And so for polonium, that is going to be, where is it? Number 84. So that's 84. And so here is our parent isotope, and it undergoes alpha emission. So it's going to release an alpha particle, which is the nucleus of a helium atom. So we know that something is going to be produced. So we're going to get a daughter isotope plus alpha particle. So alpha particle is the helium nucleus. So we can either write He for helium, or you could put the alpha particle. So you could put that symbol for your alpha. It's up to you, but helium is fine. So it's going to, since it's 2 protons and 2 neutrons, that's going to be a mass of 4. So mass number of 4. And so protons, the atomic number goes on the bottom. So it has 2 protons. So that's going to be 2. So here is our alpha particle, and here is the polonium-210 that we started with. So we need to figure out what this is. Well, the way to do this is to remember that the top number on both sides always add up to the same number. So since we have this side has the top being 210, then that means that whatever this value is here plus 4 has to equal 210. So let's say I put in x. X is some element. We'll figure out what x is in a moment. But since this side has a total of 210, then something plus 4 has to equal 210. So that means that we subtract 4 from 210, we get 206. So 206 plus 4 is 210, so that's equal there. So we know that this number has to be 206. Now, the same thing for the bottom numbers. So the total bottom number on this side has to equal both bottom numbers on this side together. So something plus 2 should give us 84. Well, what plus 2 gives us 84? That's 82. So now we know the bottom number. And again, remember the bottom number is your atomic number. The top number is the mass number. So remember, atomic number tells you the number of protons, which also tells you the identity of your element. So since we know that the atomic number is 82, we look up 82 on our periodic table. So right here on our periodic table, number 82 is lead, Pb. So we got lead here. So we're going to erase this and we're going to put Pb. And there, ladies and gentlemen, is an example of a nuclear equation that we put together. Okay, let's try number 2. In this case, it says write the nuclear equation for the reactive decay of radium-226, again by alpha emission. So we're releasing an alpha particle again, which is going to be the same here. So we're going to start with radium-226. So radium, which is Ra, 226. So 226 is the mass number. So that's going to go on top here. And so let's look up radium. Radium is number 88. So that's going to go down here. So that's the atomic number, and this is the mass number. So that's going to, again, emit a particle. So we're going to get a daughter element. So this is the parent element. This is what you start with. And this is the daughter element. Plus, we're releasing another alpha particle. So again, He. Well, let me do alpha. I'll do alpha. So I'll write alpha this time. So here, that's the alpha symbol. And again, for 2. So again, it's a helium nucleus that has 2 protons and 2 neutrons. Excuse me. So both of those together, 2 and 2, gives you a mass number of 4. And again, the atomic number is only protons. We have 2 protons, so that's 2. And so that's the alpha, Greek symbol alpha. I know it looks like a fish, but that's alpha, my alpha. So this is your alpha particle. And again, both sides have to balance. So the top numbers have to balance. So I'm going to put X right now. So both of these numbers here must add up to 226. So what plus 4 gives you 226? That's going to be 222. So 222 plus 4 gives you 226. Same thing for the bottom number. The bottom numbers have to add up to the same on each side. So whatever is the total on this side has to equal the total on this side. So total on this side is 88. So what plus 2 gives me 88? That would be 86. So 86 plus 2 gives me 88. So that's equal to this side. So in order to figure out the symbol, we look up 86. That's the atomic number. Mass number on top, atomic number on the bottom. So let's look up our example. So 86 is radon, Rn. So 86 is radon. So that's going to be Rn. And so this again is our complete nuclear equation for this decay. So this alpha decay of radium-226. All right, let's do our next one. So here we want to write the nuclear equation for the radioactive decay of zirconium-97 by beta decay. So beta decay, you have to remember is the release of an electron by the nucleus. So what we're going to do, because we're going to call that negative particle a beta particle. So we release a beta particle, which is basically an electron from the nucleus. And so we need to describe that by an equation. So again, we start with what we're given. This is our parent isotope. So zirconium, so Zr97, that's the mass number. So that's going to go on top here. And then we look up the atomic number on our periodic table. If I can find that really quickly. Zirconium is one of those ones that we don't work with very often. Where is it? Where is it at? There it is, number 40. So number 40 on the periodic table. So that is the atomic number 40. Okay, so here's our parent isotope. We're now going to draw our equation, complete our equation. So it's giving off an a beta particle. So we're going to end up with some other daughter isotope plus the beta particle. And so the beta particle can be written like this. Since it's basically an electron, you can have E. And so since the mass number is on top, electrons have 0 as far as AMUs go. So we'll put a 0 on the top because that's the mass number. They practically don't have a lot of mass. So it's practically 0. And then the negative here for the charge, right? So that's a -1. So this is the symbol for your beta particle. You can also use this symbol here, right? So that's your beta symbol. You could use that. So it'd be 0 on top and -1 on the bottom. So either one of these is fine. So what would this element be? Again, the top numbers on both sides. The top numbers on both sides have to equal. So we have 0, this number, and this number. So what plus 0 gives us 97? Well, 97. So we have 97 here. So 97 plus 0 gives us 97. So 40, we have 40 on the bottom number. So 40 on this side, we have to have 40 on this side. So what minus 1 gives us 40? Well, that's going to be 41. So 41 minus 1 gives us 40. So here's our element. 41 is the atomic number. So we look up 41 on the periodic table. And there we have niobium. So NB. So our symbol is capital N, small b. So this is the equation of the nuclear reaction where zirconium-97 releases a beta particle, and this is what you're left with. Okay, I'll do one more, but I have to erase my board. So I'm going to erase this one. And so my last one I want to do is, what do you do when you go from, oops, let me use a different color, carbon 14 to nitrogen 14. So the question is, what kind of decay are we going through in order to make this transition? So here we have our parent isotope, and instead of giving us the decay and the particle that's decaying, the particle that's being released, they're giving us the parent isotope. So instead of giving us this, sorry about that. So instead of being given this and this, we're given this. So this is our daughter isotope. So we begin the exact same way. So carbon 14, so the element is C, the symbol is C. 14 is the mass number. Look up the atomic number of carbon on the table and you get 6. So number 6 on the periodic table. So here's our parent isotope, and it's going to break down into this daughter isotope. So it's nitrogen 14, so it's N. Again, the mass number is here, so that goes on the top there. Let me write that better. And then nitrogen, we looked that up. I believe that's 5. No, that's 7. So this one is number 7 on the periodic table. So that has 7 protons, atomic number 7. So now we want to know what particle is released for this decay, and that will identify what type of decay we have. So remember, so the 2 top numbers here on one side has to equal the total top number on this side. So the total here is 14. So 14 is the same. So 14 plus what gives us 14? That would be 0. And then here we need 6 on this side. 7 plus what gives us 6? Well, that's going to be -1. So that's -1. So what particle has 0 for the mass number, -1 for the atomic number here, or this bottom number? Well, we just saw that. It's this one here. It's a beta particle. So that means, and this time I'm going to use the beta symbol. So I'll use the beta symbol. So that means that this is beta decay. So that's how you write your nuclear reactions. Remember, the key is everything on the top, the top numbers on this side of the equation has to equal the total top numbers on this side. And the total bottom numbers on one side of the equation has to equal the total bottom numbers on the other side. That is the key to writing and balancing your nuclear reactions. Thank you for joining me. I hope you enjoyed the video. If you enjoyed my videos, please like, share, subscribe to videos. Hit that like button. Hit that notification bell so you'll be notified. Subscribe to my channel. And put a comment in the comment section so you can tell me what you think, ask questions, and I will answer your questions. Thanks for joining me. Have a great day.